Thank you. Yeah, hello everyone. Welcome to the second half of this meetup. I hope you had a really nice break and maybe got to talk to some people you haven't met before here. I see like a good mix of familiar faces and new ones, which is really cool. I think it happens with all these meetups. My name is Petter. I've been coming to these meetups since the first year in 2017 on a semi-regular basis, and it's been really cool. Learned a lot of nice things about C++ and met a lot of really nice people here. So also from time to time I have done a talk here because without the talks there will be no meetups. So I really recommend you to try it out. It's great. Now we can become a pro member of the group as well, which I think was really nice. This is actually my 5th time doing a meetup here, talk here, and looking back at my previous talks, I realized that they have all had something to do with concepts. So the very first one I did back in 2017, this was all about concepts. Back then it was a feature that we all thought would be in C++ 17. It didn't quite make it in time, but instead we got a much more polished concepts in C++ 20. Then I did a small lightning talk about type functions, which is an idea related to concepts. Then I did a talk which was basically about fundamental concepts of algebra in a kind of C++ context. So this was this also where the idea of concepts comes from originally. And then last year at this location, I presented a little functional parsing library that I wrote in C++ 20, and where I had a lot of use of both of the standard library concepts, and I added 2 concepts of my own to make the code much more readable, in my opinion at least. Yeah, a while ago when Harald asked me to talk about concepts again, first I thought, haven't I talked enough about concepts already? I don't really know if I have that much more I want to add. But then I thought that actually I've used concepts for a while now. I'm not an expert or anything, but I feel at least confident using this feature. And along the way I have picked up on a few things, learned some tricks, and it also made me look at C++ code in a whole new way. So these are things that I think are worth talking about. This could be useful to others who are starting to use concepts in practice. So this is really not like a technical introduction to concepts. I won't talk about all the different syntaxes or how to implement your own concepts really, or how the standard concepts are implemented. This is more focused on just using the standard library concepts effectively, because it's also where you will be starting out anyway. And there are already many great talks about these subjects, so I hope this will be a complement to that. Okay, so let's start with some terminology. I think there are 3 C++ terms that are important to know about when you use concepts. First of all, because they are things that will show up in your compiler error messages. They are also used all over the place in the standard and in documentation and so on. So first of all, concept. So one way you can look at a concept is that it's a named set of type requirements. So you have a bunch of requirements on a type, and they can be of different kinds. So they can be syntactic requirements, saying something about what must be included in the public interface of this class or this type. But they can also be semantic, so saying something about how is this type supposed to really work when you use it with this public interface. Sometimes the requirements can be of a more contractual nature, something about the limits of when this semantics work correctly, like preconditions, postconditions. And there can be complexity requirements, so like performance guarantees on certain operations on a type. And many concepts are about just one single type, but it can be, you can also have multi-type concepts, and then they can express how these types are connected together. And yeah, then a model, that is the term used to describe a concrete type, or in the case of multi-type concepts, it could be a certain combination of types that fulfill those requirements of a concept. So then we say like it's a model of that concept, or it models that concept. Sometimes you also see model satisfies a concept. And then constraint. So constraint is specifically when you put requirements on template arguments. And usually those requirements are expressed as concepts or a combination of concepts. So here's one example. There is a concept in the C++20 standard called integral. And the requirements of that concept, essentially it defines it as a set of built-in integer types. And there are many, many such types, of course, in C++. This is not all of them, because you can have combination of const and volatile and const volatile before all of them, and so on. But these are some of them. So you can sort of look at it as a set. The concept describes this set of types. And there are also two more specific types for the signed integral and the unsigned integral that divide the set into two subsets. So here, like the type int, it models both integral and signed integral, and also many other concepts. But it's not an unsigned type, so that has different semantics, so that is not an unsigned integral. So when you actually use a concept to do type checking, then you can more like think of it as you're calling a function, a compile time function, that you pass in your type and it gives you back a Boolean. Now in sort of an ideal world, that Boolean would tell you, is this a model of the concept or not? In reality, it's not quite that simple. If it returns false, then yes, you know that your type does not satisfy the concept. If it returns true, then sort of the best thing you can say is that it probably models the concept. And the reason is that really all you can express in C++ code is syntactic requirements. And that's the only thing the compiler can check at compile time. So those syntactic requirements will have to sort of stand in for all of the other kinds of requirements. But it's important not to forget this, because first of all, you shouldn't view concept as some magical feature that prevents you from writing bugs. You can have a lot of errors in your implementation of type or use still. But it's important when you look at the standard concepts that all these other requirements are in the standard. They are written in form of documentation. So if you design your own concept, don't forget about documenting semantics and that kind of thing that we cannot check. Okay, so where are concepts useful? Well, you probably heard that they are supposed to give you better error messages when working with template. It's an age-old problem with templates in C++. And perhaps they can improve your compile times, at least comparing to using metaprogramming, enable if techniques, and so on. And it's pretty easy to see why, right? So here we have a function compute. It's a template, takes any type t. And maybe there's lots of code in this template. And when you instantiate it with some type, maybe all of that code compiles, but at the very last line, there's a plus. There's an addition, and that type doesn't support addition. Maybe you passed in a vector, for example. So then, of course, you get a very long and hard to read error message, especially bad if the type you passed in is also derived from a template, because then it goes into the implementation details of vector or something like that, it's pretty terrible. But but suppose this function was only supposed to work with built-in integer types. So then you can constrain it and write something like the second version. And now, if I try to pass in a vector, the same, the error, because vector is not an integral type, we will catch that before even instantiating this template. Of course, that's just a check on the interface, so don't forget that you can still write lots of code inside that doesn't work with the integer types, and you will still get errors that way. You could also actually you could have both of these templates side to side in the code. Even if int would support both of them, it will not be ambiguous, because the more constrained version with the concept will be preferred. Yeah, so why do we write templates? Well, I presume that a lot of the time we're just thinking that we do it to avoid code duplication, because maybe we read this book and we heard about the dry principle, which is a really good principle. That is not actually all about code duplication. It's about documentation, databases, API documentation, whatever you have, this is a common problem. So if you use templates to implement the dry principle, you have this problem with the error messages. But of course, there are other ways to do this in C++. So I thought it was maybe interesting to compare it to sort of the classical object-oriented approach. So here is just like a typical example of a class hierarchy. Maybe you have some user interface widget library with an interface class, and then we have some concrete classes that implement the interface, like a button, a text box, and so on. And now we can write sort of generic code. If you have a pointer or reference to a UI widget, we can draw it, and so on. And without actually caring what particular type we're coding against. So this idea of an interface is very closely related to concepts. But there are also some interesting differences that I like to point out. So first of all, for this button class, for example, to be a UI widget, it has to be explicitly state that it is, right? You have to inherit from it. And so that means your button will have to have access to the definition of UI widget. You will have to design your interface before you implement the class. And also, of course, with class hierarchies, we have virtual member functions, which means there is a small overhead. So when we call the function, we have to go through a virtual function table. We also have to store a pointer, a hidden pointer assigned to the class. Of course, it's a very small overhead. It's usually acceptable, but it is there. And then we have, of course, with a class hierarchy, it's all about the member functions, really. That's the only thing you can override. So this can be a problem when you have functions that take multiple types, like a binary operator and so on. It's not quite so natural to use with class hierarchy. So object-oriented programming, it's great, but with certain limitations. So suppose instead we wanted to implement this using a UI widget concept. Then it's a bit different. So the class button, for example, it's an implicit relationship to the concept. The button does not have to, it doesn't state that it is a widget. It doesn't even have to have access to the definition of widget. It's something you could design in the future after you have your button. And of course, there's no need for virtual functions. You can have virtual functions. Concept works together with OOP as well, but the overhead is optional. Also, now this text box class, it doesn't have a common type with the button that you can convert them to. So you can store them together in a container, for example, without using something extra on top. Yeah, you have to rely on templates to call the right version of the function. So something I think is quite useful if you implement a type that you intend to model a concept, just put a static assert below the type. There's two good things about that. First of all, it's documentation. You state your intent. And it gives you a quick check if you remember to implement the whole interface correctly. So like if I made a mistake, like here probably in the text box, I should have said on select instead of on click. So then we would catch that error early on. Right. So which are the concepts that you should start using? So there are many concepts in C++20 standard library. Many of them have to do with the ranges library. But if you just include the concepts header, you will get access to 30 concepts. And these are the ones. These are like the core concepts of the C++ standard. So I think it's a good idea to get familiar with these names, learn them, and try to guess what they mean and see if it's what you think it is. Actually, I don't think this is hard at all, because like if you know the fundamentals of C++ type system, if you're familiar with using containers and algorithms in standard library, this pretty much describes things that you already know very well. So for example, like a copyable type. If it's a class type, that means it has a copy constructor, a copy assignment operator, and it makes copies without changing the original. That's basically what it is. So you can constrain template functions, but you can also constrain template classes, and usually you would want to do that as well. But there are a couple of exceptions maybe. So I thought it was kind of interesting, so I made up this example. Suppose that you have implemented your own container. So my vector here is some version of vector. It doesn't matter how it's implemented, it's just a container. And now suppose I want to use this vector to implement another data structure, a tree of integers. So int tree has a root, which is an int, and then it has a number of subtrees, which of course are also by themselves int trees. So it's a recursive data structure, and this works fine in C++. It will work exactly like you think it should work. But suppose now that I decide that I want my vector to be constrained. So I want it to only work for copyable types. So I put a constraint on the template, and now suddenly the class doesn't compile. So if you cannot see why, then I think it helps to, like, imagine you are the compiler and you're going to look at this. You see this struct int tree, so you want to figure out what is the data layout of this class. So first there's the root, it's an int, that's fine, we know what that is. Then we have a subtrees, which is a vector of int tree. So we have to look for a template to instantiate that type, and we have it, but it's a constrained template. So we need to check the t is copyable. So what is t here? Well, t is int tree. That is a type that we don't have yet. It's an incomplete type. We are in the middle of compiling int tree, so we cannot check if it's copyable. Maybe copy constructor is deleted further down in the class. So it will break the code. And so why did that actually work before? Well, it works because the compiler can do a little trick. So if you have an unconstrained template, sure, we don't know what int tree is at that second line in the struct, but we know that it is a class that we are in the middle of compiling. So we don't have it yet. We will know everything there is to know about int tree as soon as we just get to the end of the struct. So we can wait with instantiation as long as we see that there is a template there. And so then at the end, when the struct is complete, then we can figure out, yeah, okay, my vector int tree is just a pointer and a size t. So we have the complete class. So Some of the standard library containers are designed to work with this kind of incomplete type. I think it's vector, list, and forward list are required, but your standard library may have other containers as well doing this. And so this is a great feature, but it means, unfortunately, that if you do something like on the bottom here, a static assert that a vector of some move-only type is copyable, it will say true. And of course, a vector of a move-only type is not copyable, but this is only checked on the interface. So of course, vector has a copy constructor, a copy assignment operator. It's only when you're trying to instantiate those that you will end up with issues with a move-only type. So it's a little surprising, a little unfortunate, but you really have to choose either support incomplete types or constrain special member functions like this. So yeah, I thought it was a little interesting anyway. So we can't really, I should also mention this is not really a problem just with constraints. So if you use enable if, you will have exactly the same issue. And so you can't really put a constraint. The next best thing you can do with this, I've done this sometimes, is put a static assert in the beginning of your function as early as you can. That way you can at least get the error earlier, and you might even want to put your own error message there, which might be a lot easier to decipher. So this is not a constraint. It's in the implementation, but it's also a use for a concept. Right. So also want to kill the myth that concepts are only interesting if you have templates in your code. Like many code bases don't have a lot of templates, maybe none at all. But you can still have a lot of use for concepts in C++20. So here's just a free function with no templates. But so the idea here is that we just want to find the currently selected button and redraw it. So note that I used the ranges version of find if here because the ranges library is constrained by concepts, unlike the old algorithms. So immediately, like if I pass in something, if buttons is not a valid range, like a container maybe, and if is selected is not a valid predicate on the value type of that range, then I will get a compiler error message that won't go into the implementation of find if. It will tell me in a much better way what's wrong. Also, I used auto for the return type here because it's an iterator. I can't be bothered to type out the full type of the iterator. I don't really care what kind of range buttons is here. And of course, ever since auto was added to the language, everyone has been fighting about when to use it and when not to use it. But I think, at least for iterators, everyone pretty much agrees that it's good. But if I change the find if to some helper function and it doesn't return an iterator anymore, the return type is just deduced, and I will get an error at a further point in the function, which might not be great. But something you can do with concepts, if you have a single type concept, like forward iterator, for example, you can put it before the auto there. And that's quite a nice middle road between being explicit and still generic. So here I put forward iterator because I probably want to call this multiple times. And buttons is probably some kind of container. So I think this is a nice way to start introducing concepts in your code. Speaking about iterators, so since the ranges library needed iterators, there are 6 iterator concepts now in standard. And they pretty much correspond to the old iterator categories that we all know. They're called named requirements and things like legacy input iterator now in standard, I think. But what's good to know about this concept is they are similar but not quite identical to the old requirements, because there was a chance to improve on the iterator definitions thanks to new features in the language and user experience. So a good thing about that is that it's much easier now to implement your own iterators. That used to be quite difficult, figuring out if you actually did everything correctly. So this is just an example to illustrate the minimal interface for an input iterator. So it's just a wrapper around the pointer to some array, but restraining the interface to the minimum I could do. So iterators have a lot of associated types, but now you only need to define two of them, value type and difference type. And another interesting thing with input iterators is that they are not required to be copyable. So all the input iterators were copyable just because they were invented before we have move semantics. But now you can actually delete the copy special member functions, and here I just defaulted the move. And actually, like, making copies of input iterators never made any sense if you think about it. Like, you have an iterator, and then you make a copy, and then you advance the original one. Now, what does it point to? Something that has been invalidated. And yes, you may be able to advance it, but you're not even guaranteed that advancing it will end up in the same place as the original. So really only the useful thing you can do with input iterator copy is to reassign or destruct it. So algorithms using input iterators never use copies. And yeah, you need to be able to dereference, like before, only the read version, because it's input. You need both pre and post increment. You should never ever use post increment, but it needs to be there to support code written by people who don't know better, basically. So, but note that it can return void. There's no requirement on the return type, and returning something for an input iterator wouldn't make any sense. It's like a copy of the old value. So you don't want that. And yeah, so I think it's good to have classes like this just lying around as a reference. You can go and look at them and remember what you need to implement. It's also quite useful for like unit tests. You can just take an array and use this as an adapter to test against input iterator versions of some algorithm. Okay, so that was like a mix of things from all over the place. So in the second half, I wanted to have a concrete example, implementing a very simple generic algorithm, but like with concepts at the top of mind. So I needed to find a really, like, good generic code always comes from good non-generic code, some concrete implementation that does something useful. So I decided to look at something in this book, classic book. I'm sure many of you have it at home. One of the cool things about this book is that there are many examples of functions that is in the C standard library, so you can see a possible implementation of them. So it's very instructive in that way. And one of the very first functions that pops up in this book is this one, strlen. Very familiar function, I hope. It gives you the length of a C-style string. And something cool about KNR is that there are 3 separate implementations of strlen in the book, and they are all different. So it shows you 3 different ways to do it, and they're all like used to illustrate different things. So this is the first version of strlen. It's already in chapter 2, and this is before we learned about pointers, by the way. So it takes a string as an array. We have an index. It's initialized on a separate line because this is old style C. It checks the character at that index. If it's a null character, we exit the loop, and so I will contain the string length. So this is really just to illustrate how strings work in C. But of course, we know that arrays really decay to pointers inside the function, so you can do this with pointers as well. So in the chapter on pointers, page 99, is the second version of strlen. So this one has a pointer, so it's a bit clear in the comment that it should be a string pointer. And instead of the index, we have a counter n, and instead of the while loop, there's a for loop, I guess to make it more compact, where we use array dereferencing, and we increment both the pointer and the counter. And this works as well, of course, but it's a little bit inefficient. We don't really need to do 2 increments in the loop, right? Because we have pointer arithmetic. So like just 4 pages later, where it explains pointer arithmetic, is the last version of strlen. So here we just take a copy of the beginning of the string and advance that pointer, and then we return the difference. So this is like the best version, the most efficient one, so I want to generalize that. So before even moving to C++, we can do some things. Like first observation here comes from Alex Stepanov, who father of STL. In his courses, he used to teach a few good programming principles. One of them is called Law of Useful Return. A procedure should return all the potentially useful information it computed. So the idea is if you have a function and it does some kind of work internally to get some intermediate result it needs, you should always think, could the caller be interested in that value? Because it might be that the caller can get it but has to do extra work to retrieve it. So you should return it when you can, or you can do something else. So here, where's all the work happening? It's in the loop, right? That's all our programs just spend time in loops. So that's where the work is. And what does the loop do? Well, it calculates the end of the string. And then we just use that to calculate the length. But maybe the caller was not interested. Maybe the caller called this because they want to do something at the end of the string. They know the beginning, and now they know the length. And they can add it to the beginning, and they will get to the end. But we already had it in the function. So it's extra work. So what can we do? Well, we can split this function. Just take out the loop part as a separate function, and then we can refactor this. So let's just do that. And so now I call this function findEOS. So it just finds the end of the string. And if you look in the implementation, you should notice that we can actually remove the copy p there, because we get it from the parameter, just getting it back to as efficient as before, at least assuming it's inlined. OK, so that's good. But now look at the loop. It's doing something very specific. It's looking for a null character. So maybe we could be interested in looking for another character in the string that we know is there. We just don't know where. So let's make that a parameter as well. So we get find char unguarded. So it just looks for a character. Of course, this function is unsafe. So you can say what you like about that. But at least I named it unguarded to make you aware of this fact. And I added the precondition. Of course, this C has to exist in the string. Otherwise, we will run off the end and bad things will happen. But when you're looking for the length of a string, it's what you want to do. So you have to use it carefully, let's say. OK, so that function, it just works on character arrays. But of course, there's nothing in the code that prevents it from working on an array of int, or float, or boolean, or whatever you have. So it's time to go to C++ and make it a template. So I just cleaned it up a bit, changed some names, and made it a template. So it looks more like C++ code here. Well, it is C++ code. OK, so this is good. We implemented the dry principle. So we're done. Well, no, we're not done. This is where the real work begins. So now we have to figure out what is the requirements on this type T. It cannot be anything. It has to be something. So a good start is just look at the implementation and see what we use. So we're taking pointers to T, so it at least has to be some type that we can construct somehow. We have to take addresses. The value we look for, we take it by value, so that might be a copy if we pass in a variable. And you will probably want to support that. And we're doing this inequality comparison. So of course, now we can think, okay, inequality comparison doesn't need a copy. So we can take or a constant reference instead. And that makes it better for big types. And we get rid of that requirement as well. Okay, so now think about like what is the simplest possible type that would work here with this implementation. So it would look something like this. So my minimal type, it is something, and it has an inequality operator. So this will compile. But I don't think this is a very good type. There's something missing here, and I'm not talking about the implementation. So if you don't see what's missing, it helps to think of another good programming principle, the law of completeness. When designing an interface, consider providing all the related procedures. So the idea is that some functions don't come by themselves. They belong in a set of related functions, and they should always be defined together. And it's easy to see why here, because suppose we want to, this function modifies two objects of my minimal type, and maybe I want to have an only modify if they are not equal. So I would have to write if not t not equals u. That's not a very natural thing to write in C++. Right? We all know for built-in types this should be replaced with if t equals u. That's sometimes you need unequal, sometimes you need equal. So we should design our types to allow such code transformations that we are used to working with built-in types. So really we should have both operators. And that's actually required by the concept equality comparable. You need to have both of them. Also now in C++20 you can default equality, and you will actually get both functions implemented. Same thing with the spaceship operator, so it's really like the way it should work in C++. Okay, great. So we can constrain this with equality comparable. And now we'll get rid of some of the bad error messages. We won't catch errors too late. Of course, this doesn't support this incomplete type that I had, but an important point here is the purpose of the constraint is not to specify the implementation, it's to specify the meaning of the algorithm. We don't like under-constrain a function just because that's minimal needed for this implementation. We want the freedom to change the implementation to use equality here. So it's a bit subtle, but it's good to think about. Okay, so what does equality comparable really mean? So if you look in standard, it says there's a syntactic requirement. You need to have both, and they don't need to return bool, but they have to be convertible to bool. Okay, so that's easy. There's also semantic requirement, also pretty self-evident. They should implement equality, whatever that means for a type. Even if you can implement something else, don't. It's reserved for this particular function. If you implement something else, you get the errors, compiler errors you deserve. Let's just say that. There's also a contractual requirement here. So it says that the expressions must have the same domain. Domain means the set of valid input values for these operators. So it's perfectly okay to have equality with preconditions. You can have a type with some special odd values where equality is not defined. So an example of that would be floating point numbers with the nan values. Yes, they are defined, but they don't work as equality, so it's really a precondition. So you can have types like that. That's okay, but if you have a valid value for equality, it has to be valid for inequality and vice versa. Otherwise, you cannot safely switch these operators. Standard also says that expressions must be equality preserving and stable. Stability is actually part of equality preserving. What that means is if you call the function multiple times with equal inputs, it always returns equal values as the return value. So you cannot have equality that alternates between returning true and false. That would make no sense. Stability means that actually if you pass in the same object multiple times without changing it in between, there should be no side effects. It should not be modified or anything like that. So really, if we didn't have that, we couldn't reason about equality. We couldn't write an if statement if you can't trust it's true on the next line in the code. So it's also pretty evident. Even if you follow all this, you can make mistakes. So this function has a bug. So my type, I decided that objects are never equal. Can you see why this is wrong? Maybe if I put a unit test like that. So I just create an object T and check, is it equal to itself? In like any logical universe, objects are always equal to themselves. So if they're not, then you're going to have even more bugs. So what if you put true there instead? Does that function have a bug? Can you think of some type where this might be okay? So, what? Yeah, exactly. Like a type that only has one logical value in it. Like bool has true and false, but if a type can represent just a single thing, then this is perfectly sensible. It's a no-op to do equality, always true. So like there's even more. There's these like mathematical requirements. I think it's easiest to express this in a unit test, something like this. So inequality is the inverse of equality. Equality is reflexive, equal to itself. Inequality is anti-reflexive. We have symmetry, so order of operations don't matter, and transitivity of equality. So T equals U equals V, then you know that U equals V. You never have to check that, except for maybe in a test. Right. So there's also a complexity requirement here. And this is actually, I should say, not in the standard. I don't know why the standard doesn't talk about complexity requirements for concepts like this. There might be some reason. I don't think it's I think it should be there anyway. But so your equality has to be somewhat fast. It shouldn't be worse than linear time. So if you cannot implement equality efficiently, you can't really use any algorithms efficiently. So then maybe you have to go back to some simpler definition of equality, or just don't support it. Okay, so that was a lot of stuff just about equality. So like when you dig into the fine details, it's really complex. But I think this also illustrates the power of the standard concepts. Like if I put equality comparable there cannot be any like philosophical arguments about what equality means. It's defined in the standard. We must all agree on that. That's what makes our code work together, right? So, and we just have that name we can all share. Yeah, so the next step, you probably thought of it already. We don't want to just work with contiguous ranges, arrays. We want to work with iterators to generalize this. So we just replace our pointer with an iterator type, and now the work starts all over again. So, okay, what are we doing with iterators? So we take it by value. That's just a convention. Iterators are always lightweight. We are dereferencing, but only for reading. And we are pre-incrementing. And we're also doing this just once in a loop. So which iterator concept can we use here? Input, exactly. So we know that. So that's pretty good. That was easy. So now we constrained all our types. But there's something still missing here. So now that we have two types, think about, are these types completely unrelated in the code or not? No. These types are related. So they interact in the inequality comparison when we dereference. So we don't want just any input iterator. We want an input iterator. We're thinking of input iterators pointing to T. But there's one more law here that's good to think about. The law of separating types. Do not assume the two types are the same when they may be different. It's a common mistake in templates to use the same template type when you don't really have to. So we really want something more like this. The iterator's value type, which we can get with iterValue t, it doesn't necessarily have to be t, as long as it is equality comparable with t. So that's a more general concept that allows equality between two different types. So that's a bit better, I think. So, okay, I could generalize this even further, but I think this is a good point to stop. I just want to make a final remark about performance versus safety. So you might think, okay, this is a very unsafe function. We shouldn't have it. In C++, we want optimal performance, but we're also very concerned about safety. And often these two things are seen as conflicting, but not always. So Donald Knuth, a long time ago, observed that you can do a faster linear search than we do with find, standard find. That algorithm, of course, do two checks in the loop. Check for the object we're looking for and the end of the range. But we can get rid of one of the comparisons by doing this. So it's very simple. We have a string, and hello world, we're looking for the capital A. So we won't find it in a string, so we cannot call our fast unsafe function. But what we can do is we can ensure that it is in the string by swapping the last element, right? So then we satisfy the precondition. That kind of element is usually called a sentinel or a guard or dummy record or something like that, which enables us to do find unguarded. We know that we'll find A. Might be early in the string. It might be at the end. After a search, we need to restore the string. And then we have one final check to do. So it might be that we found a real A in there, but if we come to the end, it might have been that the exclamation mark actually was an A. So we need to do one final check at that line. Yeah, so this is my attempt at implementing that algorithm. Find guarded. So it takes an iterator range, first and last, and the value you're looking for by values, because we need a copy. First, we check if it's an empty range. Then we just return first. Otherwise, we have a non-empty range, so we can go one step back from the end and swap in our sentinel. Then we call find unguarded. We restore the range, and then there's a final check for that final place we end up. And if it's not equal, then we can advance once more if we're at the end. But so this could be faster than standard find. But standard find works on input iterators. It doesn't need to modify the range. It only does a single pass. Here we actually need a bidirectional iterator because we're going back, and we're also like modifying this input range by doing the swap. Also, yeah, we need the range to be swappable. We cannot have const iterators passed into this. And we need equality comparison, of course. So it has stronger constraints than standard find, but it's an optimization for a special use case when you can do these things. Yeah, so that's really the end. I just want to leave you with a recommendation, some further reading if you think this stuff is interesting. This website, Efficient Programming with Components, it's like an ebook, but it's free. It's just a website. You can go in there and read it all. This was made by Justin Miners. So what he did was he took an old course by Alex Stepanov from 10 years ago, which you can find in YouTube, but he transcribed it and rearranged it in a more accessible form and wrote lots of great annotations. So you absolutely have to read this. First of all, because it's very, very funny. It's full of amusing anecdotes and like jokes about the current state of programming and stuff like that. It's also not very long, so you don't have no excuse. And it's also full of really interesting code. Efficient components. These are template types and algorithms that are not in standard library, but highly useful. So you can steal them and use in your own projects. And it also suggests like exercises and projects you can do based on this. So really cool. Definitely check it out. And with that, I would like to say thank you for listening. Hope at least one or two things got stuck in your mind and can be helpful to you. when you start programming with concepts. So yeah, have a safe trip home and hope to see you at the next meetup. Right. Any reflections, comments? I will stick around. We can take them up there. Yeah, sure.
Early, I think it was around slide 11, where the first time you removed the base class, you just had an empty shell for the implementation. How would such an implementation look?
Yeah, exactly. So yeah, this is because of time and so on. I didn't want to show a concrete implementation. What you would use here is yeah, for this simple example, like that, remember the concrete classes can implement a lot more if they want to. You don't need to include everything in the concept. That would make sense. So, maybe you have a lot of custom functions for text boxes, but the part that you write generic code for doesn't use those functions. So you could you would put a requires expression. And it basically it's a list of expressions that have to compile for the type you test. That's how you express it. So it would be pretty simple. There's not enough space. Yeah. Yeah, but it's up to you how you want to actually define this concept. And a great thing here is that this button and text box, maybe that's not your types. Maybe that's typed from someone else's library that you are not allowed to change. But you can define a concept for it. Unlike if you have a base class and you want to change the interface, maybe you're not allowed to. So that's pretty cool, I think, for concepts. Right? Anything else? You can come down here also afterwards. Yeah.
So when you said that postfix operator
yeah.
When that is bad,
all right. Yeah, so the question is about the postfix increment, why that is. For the C types, it doesn't matter, right? They are so cheap types. The convention of the C types is that the postfix returns a value before you increment, right? If you have, that could be very useful for types that are much heavier to copy. But yeah, that's really, if you look in the standard library, all the algorithms, they will use a pre-increment because you don't know the size of the type. So my argument is being consistent with that idea that really comes from C. But the thing is, a lot of code out there just use a for loop or iterators, and you write it ++. You will never use a return value. So that's the argument why you need it in the concept. Really, it would break too much code. And yeah. And also these operators, they sort of belong together. So it's good that you can return void or not return anything when you implement yourself. So yeah, I hope that's a good explanation. Anyway.
You mentioned complexity constraints, but
yep.
you mentioned that they're not standard library. Is there a way to implement that?
So, question about complexity constraints. Yeah, they're not, as far as, I haven't checked all the concepts, but I haven't found complexity requirements. It's hard. I guess you would need performance testing, more or less. And there are different ways you can performance test as well, like counting operations or counting, complexity guarantees. There's actually some stuff about that in that efficient programming with the components, and there's a class in there for doing benchmarking. That is good to look into. Yeah. All right.